So we're going to shift the index, right? So, and again, that's something we reviewed back in geometric series. However, guys, there are two kinds of shiftings here: a complete shift and an incomplete shifting. So, a complete shifting is the one that we described at the top, where we add the if we add a quantity in the starting index, then we do the opposite in the terms in all the ends inside the series, or the reverse. If we subtract at that same quantity on the end inside of the series. All right. But then there's also an incomplete shifting. What is an incomplete shifting? An incomplete shifting is that in which we only shift the starting index. However, we cannot just shift the starting index just at will. There are certain situations in which we can do that. Let me show you where, under which circumstances we can do that. Number one, consider the series sigma n equals 0 to infinity of n c sub n x to the n. So here I'm going to do an incomplete shifting and change the term n equals 0 to an n equals to 1. That's possible without notice I didn't change the ends inside of the series, right? And then what you may ask yourself, why is this possible? Because check this out. Let me expand the series on the left hand side here. So starting at n equals to 0, this is 0 c sub 0 x to the 0 plus 1 c sub 1 x to the first plus 2 c sub 2 x squared plus 3 c sub 3 x cubed, etc. Right? Infinitely many terms. But guys, did you see what happened to the very first term, that is the one with n equals 0? Got killed, right? It got killed. So this is equal to c sub 1 times 1, which is c sub 1 x plus 2 c sub 2 x squared plus 3 c sub 3 x cubed, etc. So the bottom line here is, it doesn't matter if you shift the series at 0 or at 1, that's going to give you the exact same result. So you see what I'm saying here? Okay. All right. Let me give you another example in which we may do an incomplete shifting. The series sigma n equals 0 to infinity of n times n minus 1 c sub n x to the n. All right. Notice it starts at 0. But guys, I can also make an incomplete shifting at 1 without changing anything. Do you see why that happens? Because if I substitute the 0, the n equals to 0, that's going to give me a 0 times 0 minus 1. Everything is going to go to 0, right? Now, the same happens if I do the n equals to 1. That's going to be a 1 times 1 minus 1. Where is that going to go? 0 also. So then I can also go to 2, all right? 2 times 2 minus 1, and then the first two terms are still going to get away. So let me expand it so you can see it. So that is 0 times 0 minus 1, c sub 0, plus 1 times 1 minus 1, c sub 1, over x to the 0, right? X to the first plus 2 times 2 minus 1, c sub 2, x squared, plus 3 times 3 minus 1, c sub 3, x cubed, plus etc. infinitely many terms, right? But again, do you see what happens with the terms related to n equals 0, n equals 1, n equals to 2, n equals to 3? They vanish to 0, right? So the result would be 3 times 3 minus 1, c3 x cubed, okay, plus 4 times 4 minus 1, c sub 4, x to the 4, plus etc., right? Again, do you see how the first two terms got zeroed out? So it doesn't matter if you start your series at 0, at 1, or at 2. You're going to get the exact same result. All right? And notice in this case, the ends inside of the series are intact. We didn't do a complete shifting. Yes? No, it doesn't go to 0, but actually at n equals to 2. Oh, yes, yeah, I forgot to write that one over here. Equal to 2 times 2 minus 1, c sub 2, x squared. Thank you. Thank you. Yes, yes. Mhm. You're right. You're right. All right. Let me give you a few more examples of how that works. All right. Let's move on to the next page and have a look at additional examples to perform all possible incomplete shifting for the series below. All right. Okay. So for sigma n equals 0 to infinity of n times n minus 1, n minus 2. Do you guys agree that the term at n equals to 0 is going to go to 0? The term at n equals to 1 also going to go to 0? What about the term at n equals to 2? It's going to go to 0? What about at n equals to 3? Not anymore, right? So this means we can do an incomplete shifting. I can turn this sigma n equals 1. This is equal to sigma n equals 1 to infinity of n minus 1, n minus 2, c sub n, x to the n plus 2. All right? Also, this is sigma n equals to 2, sigma n equals to 2 to infinity, n times n minus 1, n minus 2, c sub n, x to the n plus 2. Okay, and then the next one would be 3, right? Sigma n equals 3 to infinity, n times n minus 1, n minus 2, c sub n, x to the n plus 2. But guys, can I write the series for n equals to 4? Would that be equal to the series at n equals to 4? Not anymore, right? So at n equals to 3, I no longer have the terms for n equals to 2 and n equals to 1 and n equals to 0. All right? Okay. What about the next example? Sigma n equals 0 to infinity of n times n minus 1, n minus 2, n minus 3, n minus 4, c sub n plus 3, x minus 3 to the n plus 5. All right? And well, don't even look at the c, don't even look at the x minus 3 to the n plus 1. Focus on the coefficients n minus 1, n minus 2, n minus 3, n minus 4. All right? So if I start the series at n equals to 0, do you think this will be exactly the same as the summation at n equals to 1? Because, well, at 1, 1 minus 1 is gonna be 0. I'm not gonna write the whole thing here, right? So is that equal to sigma n equals to 2 to infinity? Yes, because it's gonna go to 0, isn't it? What about sigma n equals 3 to infinity? Would that be the same? What about at n equals to 4? Would that produce a 0? N equals to 5. Yes, at n equals to 5, I'm still going to get the other terms from 4 and below to be 0, right? So it's still the same, right? So that means for this series, if we started at 5, that's exactly the same as starting it at 4, or starting it at 3, or starting it at 2, or starting it at 1, etc., or at 0, right? Because all of those terms are 0 and they don't matter, all right? They're not going to make any change. That's for the incomplete shifting. All right. Do some practice on how to do complete shifting. Okay, so we have these two power series right here. Sigma n equals 2 to infinity and c sub n x to the n minus 1. Okay, so here the instruction is that we start our series at some particular starting point. Let's say at n equals to 0, right? In this case. Well, if you look at this first series, the series starts at -2. What would you do for a complete shifting in order to have that n equals to 2 to become an n equals to 0? Okay, subtract 2. However, if we subtract 2 for a complete shifting, what do we do in all of the n's inside of the series? Add 2, add 2, add 2. So sigma n equals 0 to infinity of n plus 2, c subscript n plus 2, x to the, what is n minus 1 plus 2? N plus 1, all right? And these two series are equivalent, except that the new one now starts at n equals to 0. All right? On the next one, letter B. So letter B, well, we have a series that start at n equals to 1. What do we do to make it start at 0? So subtract 1, okay? So if I subtract 1, what do we do with the ends inside of the series? Add 1, add 1, and add 1, all right? So that'll be equal to sigma n equals 0 to infinity n plus 2 c sub n plus 2 x to the n plus 1. All right? Was that C sub n, right? That's what I meant. Yeah. C sub n. Yes, yes, yes. Thank you. There we go. All right. Well, so in some like example number 17, we want a power series starting at a particular starting index, in this case, starting at 0. However, in other cases, we may want a series to have a particular power of n. Nevertheless, the way we're going to do the shifting is going to work exactly the same. For instance, we want the two series in example 18 to have a power x to the n. However, the first series has a power n minus 1. What would you do to the power n minus 1 to make it look like an n, simply? However, yes, if we add 1 over here, we have to add 1 to all n's. But what do we do in the starting index? Subtract 1, all right? So that is sigma n equals 0 to infinity n plus 1 c sub n plus 1, x to the 1 minus 1, is that equal to 0? That's simply n. All right? What about the next one? But the next one. So for the next one, we have an n plus 2 in the power of x, don't we? Okay, so here we go. How do we make it look like just n? Okay, but if we're going to subtract 2 to the power n, subtract in the coefficient and in the subscript as well. So minus 2, minus 2, minus 2. What do we do in the starting index? Add 2, right? So sigma n equals 0 to infinity of n plus 1. Oh, wait. N minus 1, right? N minus 1. I was still looking at the original one. C sub n plus 3 n minus 2. Is that plus 1 also? Wait, I mean plus 1. And that's simply x to the n. All right? N equals to which one? Oh, yeah. Starting index. Thank you. Thank you. N equals to 2. All right. Okay, so let's see what are we going to do next. Okay, finally, we are going to add and subtract power series. So now that you have an idea of how the shiftings go, that is incomplete shifting and complete shifting, this is where we're going to play some puzzles here to group them together. However, we're going to do some of these shiftings, okay? So here is the rule number one. Rule of thumb here is we would look to write all series, okay, in terms of the highest power that you see in all series. That's your key. That's your reference, all right? Uh, well, uh, what are we going to do after we identify the highest power of X? Well, number one, you want to let's see, you may want to do complete shiftings, maybe incomplete shiftings, or also expand some terms of a series. Why is that? Well, actually the first example is the best example about it. All right, guys, number one, example number 19. Rewrite the given expression using one single power series whose general term involves x to the n. Okay, ignore the x to the n for now. Ignore it for now. We can do that shifting at the very end. All right. Now, have a look at these two series. What's the highest power of x that you see? 2n plus 1, right? Okay. The first series does not have the same exponent, right? So these two series cannot be combined together into a single one because they are not like series. That is, they do not have the same starting index and they do not have the same power of x. All right, what's the trick here? Check this out. I'm going to compare, okay, the powers. Guys, between n minus 2 and n plus 1, how many units are they apart? 3 units apart, right? Okay, 3 units apart. Okay, what would you do to match the power on the first? Okay, what would you do on the first series to match the power in the second series? You would think of adding 3 units, right? That is doing a complete shifting plus 3, plus 3, plus 3, plus 3. And then what would you do to the starting index? Okay, that doesn't sound bad, right? However, this is falling into the dark side of the power series. Okay, what's the dark side of the power series? What is 2 minus 3 right here? Do you remember ever having series with starting indices with negative ones? I think we discussed those last time. Those are the domain of a power series. At least in our class, the starting index must start at 0 and then and on. No negative powers. And you might ask yourself, well, what do we do? Okay, so this is what we're going to do. Okay, let me erase all of this. So, like I said at the bottom over here, in some cases, expanding some terms of a series may be needed. All right. So this is what we do. Expand n equals to 2. All right. So that is, here we go. 2 times 2 minus 1, c sub 2, x to the 2 minus 2. And then write the series, okay, because we stripped off the first term, that is the term related to n equals to 2. Now the series is going to start at 3, right? So n equals to 3 to infinity n times n minus 1 c sub n x to the n minus 2 minus sigma n equals 0 to infinity of c sub n x to the n plus 1. All right? Now check this out. At this point, we may go ahead and do the addition. Check this out. The addition, the plus 3 plus 3 plus 3 plus 3. And then we can already do the minus 3 in the starting index. So expanding the term related to n equals to 2, that's going to prevent us to reach the dark side of the series, right? That is this negative starting indices. I mean, numerically is correct, guys. Don't get me wrong. It's still fine. Then you can simply expand and fix the starting index. But I guess it's me being a little more puristic with the definition of a power series that it should start at 0, right? So not going to the dark side. All right. Here we go. So let's simplify whatever we are left with. So that'll be equal to 2 times 1, 2 minus 1, that equals to c sub 2, x to the 0, plus sigma n equals 0 to infinity of n plus 3, c sub n plus 3, x to the 3 minus 2, is that x to the n plus 1, minus sigma n equals 0 to infinity of c sub n x to the n plus 1. Check the two series, guys. Can we combine them together? Can we merge them into one single one? Do we have the same starting index? Yes. Oh, whoa, whoa, whoa. Yes, that's 10 plus 3. You're right. Thank you. Thank you. And n plus 2, right? So n plus 3, n plus 2. All right. Now, do we have the same starting index on both series? The same power of x? Go for it. X to the 0, that's 2c2 plus sigma n equals 0 to infinity. I'm going to open brackets. N plus 3, n plus 2, c sub n plus 3, minus c sub n, and x to the n plus 1. So I'm factoring the sigma symbol on the left and I'm factoring the x to the n plus 1 on the right. All right? So that's the combination into one single series. But wait a minute, guys, we're not done. Remember the original instruction? We want a gen series where the power of x is n, not n plus 1. How about we do a complete shifting? What would you do? What do we do to the starting index? Add 1 and then subtract 1 anywhere else, right? Inside of the series. All right? So that'll make it equal to 2c2 plus sigma n equals 0 to infinity n plus 2 n plus 1 c sub n plus 2 minus c sub n minus 1 x to the n. Final answer. N equals 1. Oh, yes, yes. Thank you. Yeah. All right. First puzzle, right? First puzzle. Let's get the next one. Right. I know. All right. What about, okay, on the next page, example number 20. Rewrite the given expression using a single power series. However, in this case, no require particular power. Nevertheless, what's going to be a reference? Again, our reference is going to be our highest power of x that you see in all of the three series. Okay, which is the highest power of it? Which n plus 2. So that means I would need to, what is that? I would need to, okay, do something with the other two series. Okay. Okay, guys. So number one, between n and n plus 2, do you guys agree that they are 2 units apart? So if I add 2 units to match the power, I will need to subtract 2 units in the starting index, but that's going to send us to the dark side of the series, right? We don't want to go to the dark side of the series. Okay. So how about expanding one term? That's gonna even out with the powers when we do the shiftings, and that's not gonna send us to the dark side. And actually, it's gonna match also with the starting index n equals to 0. So expand n equals to 1. Okay, what about the next one? All right, between n minus 1, this n minus 1 here, and n plus 2 here, how many units are they apart? Okay, if I add 3 units to make it an n plus 2, I would need to subtract 3 units to the starting index, right? Well, that's gonna send us 2 units in the dark side of the series, right? You don't want to go to the dark side. How do you fix the dark side then? Expand how many? So expand n equals 1 and n equals to 2. All right, here we go. Uh-huh. So here, okay, 3 times 1 c sub 1 x to the 1 minus 1 plus 3 times 2 c sub 2 x to the 2 minus 1 plus sigma, finally, n equals to, if we expand 1 and 2, what's the next index? 3 to infinity, 3n c sub n x to the n minus 1. Now, let's expand n equals to 1 for the second series. That'll be 1 times c sub 1 x to the first plus the rest in series. That'll be sigma starting at n equals to 2 in this case, to infinity, okay, to the infinity of same n c sub n x to the n plus the last series remains the same because that was our reference series. We do not do anything to it. N equals 0 to infinity 5 c sub n x to the n plus 2. All right. Okay, let me write down the expansions at the beginning. Whatever we were left with, that is. Okay, so that is 3 times 1, which is 3 c sub 1 x to the 0, which is just 3 c sub 1 plus 6 c sub 2 x to the 2 minus 1, that's x to the first, which is just x. And over here, c sub 1 times x to the first, that's simply plus c sub 1 x. All right? And I guess at this point, we're ready to do complete shiftings on the first two series, right? Let me do that at the same time. So let me subtract 3, subtract 3, subtract, oh, wait. Subtract 3 to the starting index and add 3 everywhere else. Is that going to produce an n equals to 0 at the beginning, at the starting index? Is that going to produce a power of x n plus 2? Of course. What about the other series? Minus 2 in the starting index, add 2 everywhere else. All right? We're almost there. Okay, guys, typically what we do is factor coefficients for every power of x. So, well, number one, okay, let me write, plus sigma n equals 0 to infinity, 3 times n plus 3, c sub n plus 3, x to the n plus 2, plus sigma n equals 0 to infinity, n plus 2, c sub n plus 2, x to the n plus 2, plus sigma n equals 0 to infinity of 5 c sub n x to the n plus 2. All right? Can we merge the three series into a single one now? Do we have the same starting index in all three series? Do we have all powers of x to be the same? Yes. All right, let me do. Okay, this is equal 3c1 plus 6c2 plus c1 times x plus one single series, n equals 0 to infinity, bracket 3 n plus 3 c sub n plus 3 plus n plus 2 c sub n plus 2 plus 5 c sub n and everything times x to the n plus 2. Yes.
Plus 2. I can then just be multiplied in, and does it all need to be x 2?
Did I? Oh, because it's a common factor here in all three series. So all we do is just generate everything into one series and whatever we multiply by that x to the n plus 2.
Well,
Correct.
just to have x
Yes.
power of x.
Correct. So that's the purpose of having the power of x to the same power in all series to combine it in a single one by factoring sigma notation on the left and the power of x on the right. All right. All right. Oh, I like the next one. I don't think. Oh, wait. You gotta be kidding. Thanks. All right. So let me change this series for something else. So this will be then. Okay, let me use a different color first. We use black. Sigma n equals 1 to infinity n c sub n x minus 3. Notice in this case, this is going to be a series centered at 3, not at 0 like the other ones. The n plus sigma n equals 1 to infinity of 4n c sub n x minus 3 to the n minus 1 plus sigma n equals 0 to infinity of 2 c sub n x minus 3 to the n plus 1 plus sigma n equals 0 to infinity 6c7 x minus 3 to the n. 4 0, not 2, not 3, no, 4 series. All right, guys, well, number one. Again, what's the highest power of x? The power of x minus 3 in this case. What's the highest power? N plus 1. So, guys, you might want to write everything in terms of powers n plus 1. Okay. I would need to add a 1 in. Okay, let's do one series at a time. Actually, guys, for the first series, if I add 1 to the power, I can subtract 1 in the starting index, and that's not going to send me to the dark side of the power series, right? So we're safe to do a complete shifting over there. What about the second series, n minus 1? How many units are n minus 1? Is n minus 1 away from n plus 1? Okay, so can I, at this point, can I a second. Okay. Can I do what is that? A plus two? That'll be minus two. That's gonna send me to the dark side, right? For the second series. So what do we do to prevent that? Expand, expand n equals one. All right. Okay, the third one, we're fine. What about the third one, it's actually the reference, right? Okay, what about the last series? If I add one to get the same exponent, well, then I would need to subtract one in the starting index, right? That's going to the dark side, right? So what do we do? Another expansion, right? Expand n equals to, what is that? 1, right? That's all we have to do. Yeah, it's more bark than bite, this one, right? Yeah, of course. All right, so expanding. Okay, then this new series would be sigma n equals 0 to infinity of n plus 1 c sub n plus 1 x minus 3 to the n plus 1. And then I'm going to expand n equals to 1. That's a plus 4 times 1, which is times c sub 1 x minus 3 to the 1 minus 1 plus, okay, the third series, oh, plus the series sigma n equals 2 this time to infinity. What is that? 4 n c sub n x minus 3 to the n minus 1. All right, the third series remains the same. Sigma n equals 0 to infinity 2 c sub n x minus 3 to the n plus 1. And then I need to expand. I'm running out of space. I'm going to go plus, okay, 6 times c sub 1 x minus 3 to the first power, all right? And then plus the corresponding series, but now instead of starting it, oh wait, we're expanding the 0, not 1. We're expanding the 0. Yes, the 0. You're right, right. So this is to the, yeah, my bad. Because we've been expanding the n equals 1 a lot, right? So I think I got stick to that. Okay, so n equals 6 sub 0 to the 0 power. So now our series starts at n equals to 1 to infinity 6 c sub n x minus 3 to the n. So let me put together everything we expanded. That is 4 c sub 1 and x minus 3 to the 1 minus 1. That's the 0, which is just 1. We don't need to write it. And then plus 6 c0 x minus 3 to the 0. That's also simply 1. Okay, so plus, okay, sigma, the first series at n equals 0 to infinity of n plus 1 c sub n plus 1 x minus 3 to the n plus 1. Okay, the second series. Okay, what do we do to the second series? Are we safe to add 2 to the power to match the n minus 1, which is the highest power? Okay, so add 1 everywhere inside of the series. I mean, add 2, not 1, add 2, and subtract 2. All right? And that's going to start at 0. No dark side here. All right? So plus sigma n equals to 0 to infinity of 4 times n plus 2 c sub n plus 2 x minus 3 to the n plus 1. All right? Plus the original series, the largest series already. I mean, the series, the largest power, n equals 0 to infinity 2 c sub n x minus 3 to the n plus 1. All right? And what do we do to the last series? At that point, also shift 1 unit. So plus 1, minus 1. All right? So that's going to give us what? Plus sigma n equals 0 to infinity 6 c sub n plus 1 x minus 3 to the n plus 1. All right? And we have the 4 series with the same starting index, with the same power of x. Can we merge them together? Okay, go for it. So that'll be equal to 4c1 plus 6c0 plus, okay, sigma n equals 0 to infinity of n plus 1, c sub n plus 1, okay, plus 4n plus 2, c sub n plus 2, plus 2c sub n, okay, plus 6c sub n plus 1. Everything times x to the n plus 1. We're not done yet. We need to box our final answer, right? Minus 3, which one? Oh, x minus 3. You're right. Thank you. Thanks. X minus 3, n plus 1.